Team 24's presentation of the Global Emergency Autonomous Response System for L3 Harris Technologies. Team 24 consists of Jonathan Papp, Avery Bennett, Ashwin Ganesh, and Aidan Finnegan. Every year, millions worldwide are affected severely by disasters. These can be natural in the form of hurricanes, floods, earthquakes, and tornadoes, or they can also be through conflicts such as civil wars, terrorist attacks, or government-sponsored genocide. In any case, these disasters leave residents of an area resourceless and often stranded in the miles of rubble and other hazards that was once their home. Victims are often left without basic human necessities such as food, water, and shelter, as well as other supplies that may be necessary for survival, such as fuel and medical supplies. Though several international aid organizations exist with the express purpose of helping victims of such disasters, it is often too dangerous for supplies and caretakers to be flown to these locations. For example, in the case of a conflict, tensions in the area may be too great to help the affected civilians, and either side may see the relief workers as a threat to their cause. In the case of a bad storm, visibility may be too low to find a safe and effective area to begin work. In either case, the safety of the relief workers is threatened. In an effort to provide disaster relief without placing the safety of workers in danger, the Robotic Systems and Disaster Response Divisions of L3 Harris Technologies have created guidelines for a Global Emergency Autonomous Response System, or GEARS for short, and have asked us at Team 24 to develop the technology. The GEARS should be able to navigate through the rubble at the disaster site, avoid dangers, and to deliver cargo to those in need. When delivering the cargo, it should be able to represent what kind of cargo it is delivering to a person of any culture or background, and should indicate when it is done dropping off the supplies. Finally, the GEARS should return to the station at home base of a map of the area, including its start and end points, the path it took, and any hazards it encountered. To help us in fulfilling the GEARS requirements, the team at L3 Harris has created a miniature simulated disaster zone where we can test our technology with the GEARS prototype. Certain aspects of the GEARS functionality, such as the indication of what supplies were being delivered and the indication that the cargo has been delivered, were not scaled down for the demonstration. However, the GEARS prototype is built much smaller, carries smaller cargo, and navigates a constructed maze instead of a disaster zone. Team 24's job was to create a GEARS prototype that successfully navigates the L3 Harris simulated disaster zone so that the technology can be scaled up and help in the engineering objective of providing aid to those affected by both natural and man-made disasters.
In order to successfully complete all of the objectives and deliverables described by L3 Harris, Team 24 created many tables and charts to better organize the tasks necessary. Organizing and better understanding the project allowed Team 24 to work in a more efficient and more organized manner. First, the team created a functional block diagram. This diagram briefly outlines the inputs and outputs of the GEARS system. It also does a good job of outlining the needed subsystems of the GEARS. From this diagram, the team was able to see the subsystems, including acceleration, turning, hazard detection, and cargo drop-off mechanisms. The team also discovered inputs and outputs, such as energy, hazard detection, cargo, and the map of the path it took. From here, the team was better able to break down the project into smaller goals. Next, the team made a technical requirements chart to better understand the requirements outlined by L3 Harris. It is important to clearly write down all of the requirements needed from L3 Harris to make sure the team delivers on what the company wants and expects. The team decided to make the features needed as follows: a drivetrain, navigation system, cargo system, and map-making system. The team then expanded on L3 Harris's customer needs and made them into measurable technical requirements. This is important so the team can make goals and measure their success. The team then made a work breakdown structure based on the technical requirements and functional block diagrams. This chart just lists out all the tasks to be done in an organized way. Finally, the team made a Gantt chart to allocate its time wisely. The timetable for this project was about 8 weeks, so the team had enough time to space out the tasks. The team also split up who would be focusing on what tasks. Jonathan and Ashwin would work on more code, while Avery and Aidan would work on more physical construction. While the team managed to follow the Gantt chart somewhat closely, construction and coding took longer than expected, and we pushed back the presentation and written report. Overall, taking time at the beginning to make these charts and to understand the project better made the rest of the project smoother and easier.
When constructing the GEARS, there were many different decision points throughout the design process. While some were more significant than others, our group employed the same basic decision-making philosophy when it came to every aspect of the GEARS design. The first major decision that we had to make was about the means that the GEARS would use to traverse the course. We had multiple options available to us, ranging from using anywhere between 2 to 4 motors connected individually to wheels to a system of gears and treads. To compare the viability of each system, we measured the turning radius of the robot with each construction. Between 4 individually powered wheels, 2 powered wheels in the front, and treads, the 2 powered wheels in the front system proved to be the most efficient when it came to turning radius. On average, the 2 powered wheel system was shown to have the lowest turning radius among the 3 systems, with an average turning radius of 32.3 centimeters. The next important decision to be made was about the specifics of the hazard sensing. Quantitative testing was crucial for this section of the design, and we put all of our testing opportunities to use. After repeated testing, we were able to calculate the ideal bounds that would allow our code to stop the robot before hitting either of the types of hazards. These numbers took a few iterations of testing to narrow down, but it all paid off in our final presentation. One of the more minor aspects of our evidence-based decision-making was present in the selection of the labels. When we were looking at potential options for the labels, we were inundated with possible options. The only way to perform evidence-based testing for this part of the design was to create a survey and collect public opinion about the potential choices for our labels.
In the final design, the team thought the most important aspect should be accurate movement. This included going straight and precise turning. Because the gears would be moving through tight spaces and precise turns, the gears needed to be mobile and agile. This means the team put extra emphasis on the driving mechanism of the gears. It had to be sturdy yet agile. The team had to go through many variations of the drivetrain to ultimately come up with a final design. The team thought of many different drivetrains, including four-wheel drive, two-wheel drive, and treads. After some testing and feasibility issues, the team decided to go with the front-wheel drive, with unpowered, treadless back wheels. This allowed the front wheels to control the gears pretty well, with the back wheels just providing stability. The back wheels were attached near the center of the robot on one non-powered motor. That motor also provided stability to the drivetrain. The front wheels protruded out more on the robot to help with turning. The pivot point on the gears was near the middle of it, which was helpful for 90-degree turning on the spot. The gears was also made symmetrical so it would not veer off while going straight.
Arguably, one of the most important aspects of the gear's design was also its sensor subcomponents. The ultrasonic, IR, and electromagnetic Hall sensors were all vital to the mechanics of the robot's design philosophy. Namely, the ultrasonic sensors were known to be necessary for movement decisions, while the IR and electromagnetic sensors were known to be needed for hazard avoidance purposes. Regarding the ultrasonic sensors, the first design the team came up with ended up being the one used in the final robot. One sensor in the front to detect walls straight ahead of the robot, and an ultrasonic sensor on either side to detect if there were walls. This proved to be the most efficient and effective design for sensing walls and lack thereof during the prototype phase, so the team used it. The team went through many different designs for the placement of the magnetic and IR sensors. It was known that they would have to be near the front of the robot to be able to sense the beacons at a far enough distance so as not to touch them. This proved difficult to implement on the first few robot designs as there wasn't enough space on the frontal carriage ahead of the pie for them to be placed. This led the team to create an almost trunk-like space on the front of the robot to carry the IR sensor and a band above the ultrasonic sensor to carry the magnetic sensor. The final subcomponent that was necessary for the robot was a cargo space. Once again, the team decided relatively early upon the design that would be implemented in the final product. This involved attaching a motor and a tray to the back of the robot, which would automatically lock in place when the code started. This allowed the cargo to be placed in for containment until the motor was unlocked, thus allowing the cargo to drop out of the tray. The team decided that this would be the most effective method as it was most space efficient to the robot design that was already decided upon. There was space for the motor on the back of the vehicle, and so it was decided that that was where the tray for the cargo had been placed.
Team 24's code team consisted of Jonathan and Ashwin. In the beginning of the process of creating our gears prototype, Jonathan was the main coder. He dealt with the basic functions of the robot, such as sensor input, motor output, driving, turning, and the structure of the main logic of the code. However, as the gears prototype became more functional and closer to being ready for demonstration, Ashwin took over as the main coder. His contributions include allowing the gears to decide how to turn based off of its environment and creating the outputting of the map of the maze. Because we knew the main code for the gears has many different functionalities and in action at once and would likely become very messy, we decided to write many of the main functions of the robot in user-defined functions that can be called in one line of the main code logic. While some of these user-defined functions were quite simple and some were fairly complicated, they all played a major role in helping the team debug and pinpoint problems with the code. One example of a very simple user-defined function is the cargo lock function, which simply turns on motor A, the motor that keeps the cargo platform horizontal. The platform then becomes locked from the rigidity of the Legos and is secure for the functionality of the code. Cargo lock's complement, cargo unlock, does something similar. It lowers the cargo platform for 0.1 seconds and stops the motor roughly when the platform hits the ground. The stop function simply stops motors B and C, which are the motors used for driving, so it stops the gears prototype. The full stop function does the same thing but also stops the motor that controls the cargo platform. The spin function is used as the indication that the cargo has been delivered. It turns the prototype left for 4 seconds and then right for 4 seconds, and then it stops. The magnet function returns an array of the output of the Hall sensor, which is useful for detecting magnetic beacons that represent hazards. Moving into some of the more complicated user-defined functions, the go forward function takes speed as a parameter, prints initial sensor readings, then sets the motor powers of the driving motors to speed while the following conditions are met. The front ultrasonic reading is greater than 10, the absolute value of the magnetic Hall sensor is less than 30, and the infrared sensors are less than 12. In other words, it keeps the gears going straight until it hits a wall or hazard and then stops. The turn function takes a direction as input for how to turn. A 0 corresponds to turning around, a 1 to turning right, and a 2 to turning left. The function then constantly checks the gear's angle and compares it to its starting angle. It turns the gears until it has moved from its starting position 180 degrees for turning around, 90 degrees for turning right, and negative 90 degrees for turning left, and then it stops the robot.
Arguably, the most bread and butter element of our code would be the decide turn function. This is the user-defined function that is run whenever the gear senses a potential obstacle in front of it, and so must decide how to turn. It takes in the direction and position of the gears, as well as the maze as a whole, to make its decision. Ultimately, the function returns a number corresponding to the direction that the gear should turn, 0 being turn around, 1 being turn right, and 2 being turn left. The first priority when deciding which direction to turn is to determine whether there is a wall on either side of the gears. To determine this, the function simply reads the ultrasonic sensors on either side of the robot. If the left one returns a value less than 25, the robot is instructed to turn right, and vice versa. If both of the sensors return a value less than 25, the robot is instructed to turn all the way around. Past this, if neither sensor detects an obstruction within the predetermined range, the function aims to instruct the robot to turn in the direction that has the most untraversed space. This is why the function needs to take in the map as an input. Using a series of loops, the function calculates a right distance and left distance for the number of... I guess that works, whatever. Using a series of loops, the function calculates a right distance and a left distance for the amount of untraversed spots to the right and left respectively, and then instructs the robot to turn to whichever direction has the most. After all of these user-defined functions, it comes time for the main body of the program. The program starts by accepting user input to determine the starting coordinates of the robot. It then creates a two-dimensional array filled with zeros with the dimensions of the maze. After this, the primary loop of the program begins. The logic of this loop is as follows. Immediately, the robot checks to see if it has already exited the premise of the maze by checking the values of the ultrasonic sensors on the right and left. If this is the case, the variable used to maintain the loop is set to false so that the robot will stop going through the maze. Next, the robot uses the go forward function to go forward until it hits an obstruction. When this happens, it records the difference in the value of the front ultrasonic sensor as distance, which effectively records the distance that the robot has traveled forward. Using this distance value, the program changes all the zeros in the spaces that the robot has traveled through to ones. At this point, the robot scans the area around it to determine if there are any hazards in the nearby area, and records them both in the map and hazards list. After this, the decide turn function is used to determine how far the robot should turn and in what direction, and this information is fed into the turn function. After turning, the direction value is updated appropriately. Once the robot exits the maze, the cargo unlock and spin functions are used to display that it is exited and deploy the cargo.
During the competition, some aspects of the Gears robot performed very well, and some performed poorly. In general, the Gears was able to navigate around a few turns, but it became too inconsistent to make it through the whole maze. One good aspect of the design was the ultrasonic sensors. The Gears was able to clearly see when it was in front of a wall. The system never ran straight into a wall, it consistently stopped before the walls. The side ultrasonic sensors also worked very well. The code logic and ultrasonic sensors worked in tandem to decide which way to turn. The system always turned appropriately to the left or to the right depending on its surroundings. The precision of the turns was also a plus. The system consistently turned 90 degrees or close to it using the gyroscope. Another objective our Gears completed was sensing the magnet. When the system encountered the magnet, it stopped a few inches away from the sensor and turned 180 degrees around. One final good thing about our robot was the cargo drop-off. The cargo system was very consistent and worked every time. Our 3D printed box was able to fit the cargo, and the box fit well on the drop-off mechanism. When the system was outside of the maze, the cargo mechanism dropped and the box fell out with the cargo inside. While the Gears certainly performed well during the competition, there were definitely improvements that could have been made. One major issue with our system was consistently going straight. When going straight for long distances, the gear system sometimes curved off slightly, getting it off track. This was due to the back wheels moving slightly off the axle. When the system turned, it would slide the wheels off-center. After this, the back wheels would act as a fin, and the system would turn towards the off-centered wheels. This caused the system to run into walls on the course. Once the wheels got off track, we could not control the system, and the rest of the run would be based off of luck. Another major problem with our code was that the robot could not turn unless it sensed a wall in front of it. For example, if the system passed a hallway to its left, it could not turn that way. The decide turn function only ran if the robot sensed a wall in front of it. Unfortunately, this motion was necessary during the trial run, so the system got stuck on one side of the map. One final error during our trial run was the infrared sensor. When the Gears approached the IR beacon, it ran straight into it. This was most likely just because of a calibration error. With more time on the course, we could have calibrated the IR sensor in order to fix this issue. Overall, Team 24 had a good performance at the Gears demonstration. The team had a good base components to accomplish the tasks at the demonstration. The team just needed to implement a few more algorithms to fully complete all tasks. With a little more testing on the course and calibration, the team is confident their Gears system could have completed all the tasks. And here's some negative aspects. And here's a video of our gear at the demonstration. As you can see, it goes down the hallway, and when it senses a wall in front of it, it turns the appropriate direction, but then it cannot exit the maze because our code did not encounter this situation.
The Gears robot that we produced for the final demonstration performed quite accurately to what was expected of it. It effectively navigated the hallways in the maze and made turns when in range of a wall. While the robot was able to do each of the specified tasks individually on their own, such as move forward, create a map of its path, turn when walls are sensed, carry cargo, drop the cargo when free of maze, sense magnetic and infrared hazards, and output the map and hazard data after the completion of the code, it was unfortunately unable to string together all of these functionalities into a successful attempt during the project demonstration. There were several small details that went wrong during the final demonstration with both the hard software and hardware that, had they gone right, we believe would have led to a successful presentation. Firstly, the software limitations. Several aspects kept the Gears from reaching its full potential, starting with hitches like an incorrect array size for the mapping code. This led to some time during the demonstration to be lost to changing this in the script. Additionally, there were some physical cases that occurred in the maze that were unaccounted for in the software design. Namely, the robot had no way of turning when not prompted by a wall directly in front of it. This meant the robot was subsequently unable to find the exit of the maze layout for the final demonstration, given that it would have had to turn to the right unprompted. Furthermore, there were some errors in mapping the robot's course when starting from the second checkpoint within the maze, or elsewhere not at the starting point. This included not being able to correctly map the magnetic beacon, as well as omitting some ones where the robot had actually progressed. On the hardware side, for the most part, everything functioned as intended. The robot successfully carried the cargo and was able to drop it when necessary. However, the back wheels were not properly aligned with the front wheels for some of the demo, which caused a varied amount of leftward or rightward sway in its steering. This made navigation somewhat difficult. An issue we never encountered before the demonstration also occurred, where the robot, when carrying cargo, would struggle to move and instead vibrate in place. We are unsure what this was caused by, but it was fixed by taking off the cargo and then putting it back on. There are several ways we would improve the software and hardware to fix these mistakes in a future version of this robot and project. Firstly, it would be extremely helpful to have a scale model demonstration maze to be able to test every possible wall pattern the robot could sense. This would have helped bug test and see that the robot had no way of navigating some scenarios. Furthermore, this would allow the team to debug the mapping system as best as possible for every possible starting scenario. Another improvement to make would be to change the wheel layout for the hardware. In an improved design, the back set of wheels would not be so able to move on their own accord, and would rather be more stable to the rest of the design. This would prevent any wayward movement and keep the robot moving straight when it's meant to. Overall, we consider the performance of our Gears design to be successful. Although unable to complete a full run, it was able to unit perform all of the tasks desired of it, and nearly make it through the maze regardless. On behalf of Team 24 and L3 Harris Technologies, thank you for listening.